The light is on.
Let's get rolling here. Okay. Recursive definitions for sequences. These are a little more interesting. So use sequences defined recursively to solve problems. So let's look at this recursive sequence. The first term is 3, t sub 1 equals 3, that's called the initial condition. And t sub n equals 2 t sub n minus 1 plus 1. That's the recursive equation. So for 2 t sub 2, it's twice t sub 2 minus 1 plus 1, or twice t sub 1 plus 2. This should be a plus 1. Plus 1. Okay? This is the idea of t sub n and t sub n minus 1. This is referring to the previous term in the sequence. So I take our first term in the sequence, 3, and you end up with 7. So for t sub 3, we take twice t sub 2 plus 1. So we take our answer from before, which was 7, and add 1 to it, and now we're up to 15. And now you can generate this sequence quickly on your graphing calculator by doing this. Well, let's skip the screen here for a second. On the TI-89, have you got your calculator?
I-89.
Good. Enter 3 and just hit enter. Now you might say, why do we do this? Why do we just go 3 and enter? So your calculator is thinking of a previous idea. Oh, now you say times 2 plus 1. Now when you just enter times 2 plus 1 in your calculator, some of you are missing out the benefit of this because you don't have your calculator. What? Are you not honor students? Right? Do you not wear your calculator proudly on your belt? I would get a special holder, right?
Such a big number.
You put it in your backpack and it gets crushed. You leave it in the foyer, it gets taken.
Keep it right here.
It gets pilfed.
I had it shipped to my brain.
When you do this, when you say times 2, what automatically appears there for you?
Answer 1.
It says answer 1. Because it knows multiplication is a binary operation. Something before and something after. So when you don't put something before it, it assumes you must mean that previous answer. And that's why we had to do this 3 enter.
Oh my God.
And then you do enter again.
Wow.
We're here now.
The light is still on.
And you should get 7, right?
Yep.
And then you can just keep hitting enter to generate this, and it's so much easier, right? So what's the next one? 15, 31, 63.
127, I think it was.
I'm thinking 255 for the next one.
Yeah, and then 511.
What the? Does that look familiar?
No.
Yeah. Yeah.
No.
Is this arithmetic?
No.
Arithmetic? No. Is it geometric? No, you got a common ratio here, it would be 7 at the start and 15 7, so no. So it's not arithmetic, not geometric, so it's a neither sequence. Extra credit opportunity, try and come up with a formula for the nth term of this sequence, okay? Because you can't use our little tricks from yesterday, right? From section 1.
Because, like, the difference between the first, like, 8, then 16, then 30.
Oh, you've noticed that the differences seem to be
Yeah.
in a kind of a sequence you've seen before. If you look at the differences, you get up 6, then up 8. No, the first term was 3, actually. This was up 4. And then up 16. Oh, up 32. I think you're onto something there. But you've come up with a recursion where instead of saying twice t sub 2 plus 1, you want to come up with a different recursive formula where the thing you're adding on isn't constant, it's a power of 2. And so that's one thing. That wouldn't get you the full extra credit. Because I'm still looking for the explicit formula for what this nth term is. Right? So, that's why it's extra credit. All right. Now, let's look at another sequence. Write a recursive formula for this. Let's just focus on this one. Write a recursive formula for this sequence. 23, 20, 17, 14. What do you notice right away? It's arithmetic and you're subtracting 3. So the arithmetic, the common difference is a -3. So our recursive definition then is the nth term is the previous term. T sub n minus 1. Now you can also do it as T sub n plus 1 equals T sub n. That'll be the same thing, as long as you have a gap of 1 in the indices between these. As long as this is 1 before. Okay? Minus 3, and there's your basic formula for recursive arithmetic sequence. Notice this is wrong. This is not the recursive formula for this sequence.
You have to write what T sub 1
Or you have to initiate it. You have to say what T sub 1 is. This is not good enough. This is just saying each term is 3 less than the previous one.
No.
Right, so you also have to get it started. It's like the whole dominoes, right?
Yeah.
You could set up all the dominoes, and if nobody tips over that first one, then they're not going to fall.
What if you jump over a middle one?
Then they're not all going to fall, John. Knock over the first one, okay?
The last one.
So T sub 1 equals 23. We need that initial condition as well. So they're a team. You've got to have both parts. Now, for the explicit formula, this is not a formula sheet. This is pre-calc H, no formula sheets.
No.
You should know this by now. The explicit formula for an arithmetic sequence now. I should see half the hands up. What's going on, people? Are you waiting? Are you waiting for the day before the test to memorize these formulas? This is not sage. John.
T sub n equals 23.
Okay, let's have the general formula.
T sub 1
Mm-hmm.
minus the negative, or minus 3 and minus 1.
Okay, again, you're not giving me the general formula.
Minus, or plus
Plus
the D.
D. Yeah, that's fine.
D times n minus 1.
Times n minus 1. We usually say n minus 1 times D.
Okay.
If you go D times a quantity n minus 1, then they may think it's D of n minus 1.
No.
Calculus, it's that way all the time.
Oh, that's.
A lot of times when people say, it won't graph, it's because you put x parentheses x minus 2 and it thinks of x parentheses as functional notation, says you didn't find that function. So, that's why we like to do that. And this is what John's trying to do there. Sub it in. 23 plus n minus 1 times -3. I'm not going to let that be the end. I want you to go further. I want you to simplify and put it in the vernacular. 23 plus -3n plus 3. So T sub n equals 26 minus 3n. There's the explicit formula. Okay?
Look,
Questions?
the light is on.
Yes, very good. Yes. Okay. Now, find the first 5 terms of this sequence and find an explicit formula for T sub n in terms of n. So finding the first 5 terms, we got the first term. The second term is 1/2 times the first term, so that's 32. And then we take 1/2 of that, 16. And so the fourth term is 8. And the fifth term is 4. There we go. There's the first 5 terms. And now an explicit formula for T sub n. Explicit formula. Explicit formula? Well, what kind of sequence is it?
It's going to be geometric.
Geometric. It's geometric because we basically have a fixed common ratio. We can change this sentence into saying T sub n over T sub n minus 1 equals 1/2. The ratio of any 2 successive terms is a constant, therefore it's geometric. Okay? Geometric. So, somebody other than John now should know the formula for the nth term of a geometric sequence.
T sub n equals T sub 1 times D raised to the n minus 1.
But we call it R
Oh, R raised
to the n minus 1 because it's a combination. Okay? What happened there? Okay. Thanks, Britt. We're ready to go here then. T sub n equals the first term 64 times the common ratio 1/2 raised to the n minus 1. And so we say T sub n equals 32 to the n minus 1. Ow!
Oh, boo-how!
Hey, where's the righteous anger people? Come on, you can't. No!
Ah!
Really, you can't do that.
Right.
But some of you wanted to, and some of you will. And let's just get this purged right now. 64 times a half is 32. But please excuse my dear Aunt Sally. Exponents must come before multiplication.
Yes.
So you can't do this.
Excuse her.
Wait, lightning bolts.
No!
I missed the lightning.
What can you do? What can you do? We could try and simplify. Look, 64 times 1/2 to the n divided by 1/2 to the first. That would be legal, right? Yeah. So is this simpler? 128 times 1/2 to the n. And now we can say 64 to the n.
No!
No! I still can't.
Boo-how!
There we go. So, yes, this, in this case I'd accept this. I don't consider this that much more simplified than the other form, so I'd take either one of them. Okay? But I want you aware of how this gets simplified and not make a mistake in simplifying the rule of the problem there.
No.
And here we go with word problem. Isn't it nice that it's all typed up already? You don't have to try to copy down my scrawl. Some of you turned it up ahead of time, some of you didn't. The population of a certain country grows as a result of two conditions. Annual population growth of 1% of those people already in the country. That's because people make babies. Some of the babies die. Some of the people making the babies die in childbirth. Some of the people at home die. There's death and there's life people.
Some people get shot.
And when we take the birth rate minus the death rate, we end up with a 1% growth. But then also 20,000 people immigrate into the country each year, even though they know there's death going on there. Right?
There's worse death in other places. Outside could not stop her.
Not outside my velocity. Okay? Catch the velocity commercial somewhere, and you'll know why I'm on it, okay? There's no. So, if the population is now 5 million people, what will the population be in 20 years? Okay? So, just offhand, is this arithmetic or geometric? We have arguments for both.
It's a mixture.
It's a mixture because this is clearly arithmetic if we keep adding 20,000 immigrants to the country every year. And so it would be arithmetic if that was it. If they kept on being imported, right? And the original population was all like elves, immortal, no death, no birth, okay?
How did they get made?
They had some births and they decided to stop it. Okay? And then you got to make sure that the immigrants coming in don't agree with that policy. Then you've got linear growth. And this is the geometric part, right? The 1% growth rate. So it is a combination of two. Go ahead.
What if we said that the 1% growth includes the 20,000 people?
But it doesn't.
Then we could just say it's geometric. And could continue from there. But the whole point is to set this up as two things. Now, let's come up with a recursive definition and we'll just do it in the calculator. So P sub n is the growth rate applied. So the growth rate is 1%. 1% of what?
Previous population.
The previous population. You have to say P of n minus 1. And you add that on to the previous population, right? And what else are you adding on the previous population?
20,000.
20,000 immigrants. Okay, like that. Okay? Now, you can simplify this then as just 1.01 times P sub n minus 1. Because 1% is 0.01. So we're adding 0.01 P sub n minus 1 plus P sub n minus 1 is 1.01.
Wouldn't it be 20,000 n instead of just 20,000?
Would it be 20,000 n? It's a recursive definition. You're not trying to come up with the explicit form. You're trying to do the explicit form right away and come up with, in year n, how many immigrants have been there since year 0. So we want this.
Recursive is basically what you do, you just want the next one.
The next one. And it's recursive because you're referring to just the previous term.
Yeah. So
Now, you can sneak an n into a recursive formula.
Yeah.
It's still considered recursive because it relies on knowing the previous term. And those formulas get a little trickier than when you start throwing both piece of n minus 1 and n into the formula. We don't have to do it in this case. We don't want to. Because it's a steady flow of immigrants at 20,000 each year. Okay. So now, how best to put this into your calculator? Here's the TI-89 approach. Take 5 million, hit enter, and then do answer 1 times. And you don't actually, if you can't find answer 1, did you find out where it is on the calculator?
You can just,
It's above the subtraction key.
yeah.
Something's down there.
You can
Sorry,
actually
Marlene?
just start typing
Right.
times.
Start typing in times, it'll show it for you. There you go. Times 1.01 plus 20,000, hit enter.
Yeah.
And do that 19 more times and make sure you get to this 6,541,000. Okay?
How to test you.
Oh, no, it's on the side too.
That's like a very. I feel like you could get messed up.
You could get messed up with that, yes. So again, extra credit if you can come up with an explicit formula for this, okay?
Is there an
I'm not sure. That's why it's extra credit, okay?
I think your room might be bugged.
Yes, it is.
I got it.
Okay, did you get there? 6,541,000? Okay. Now, raise your hand if you've used an Excel spreadsheet before. Wonderful. I want to make sure everybody's familiar with this. It's a powerful tool, especially if you want to do some of these problems and submit your homework. You can show me the spreadsheet output. But also then you might want to annotate it with what did you enter in the cells. Because that's sometimes a big mystery of spreadsheets. People think, oh, these numbers are all nice, but how did they do it? Because you have to have these formulas in the cells. So let's take a moment to shift over to the Excel spreadsheet mode.
Excel spreadsheet.
Spreadsheet approach. Here we go. Call them a spreadsheet. And here's your spreadsheet. We've got a year, right? And we've got population. Population. Let's stretch this out. Let's make sure that these things are going to give us enough figures too. So I'm going to go to the cell format and just make sure that we're looking at big numbers. Numbers, I want numbers. I want lots of decimal places. I want as much accuracy as we can get here. Okay. All right. And then let's just make these columns a little bigger. So in year 0, oh, now what happened there? I just put a 0 down and freaked out. You know, it's because I tried to do too many decimal places. Let's go back to here. We're talking about people, right? Can you really have a fraction of a person?
Yeah.
No. Let's. I think it would have if I just not done quite so many decimal places. Okay. In year 0, we had how many people?
5 million.
5 million. 5, 1, 2, 3, 4, 5, 6.
Well,
And now we want to go up to what year?
20.
20 years.
So there's something better than just going 1, 2, 3, 4, 5, 6, 7, 8, 9, 10.
You gotta use the FMX thingy,
What?
You
right?
can type 20.
In the thing, up at the thing.
What is this? Do?
Wow, that's a good percent.
No, like.
Yes, you were going to put in a rule.
Yeah,
What rule do we put in here?
That's it. You add one. It's there.
No, start your rule with an equal sign, click on the previous cell, and add 1 to it. No, it's not. No, it's not. And we want 20 years? And then I hit Control D. Okay? Now, this is the nice thing about spreadsheets. They're very handy at doing recursive formulas. Because instead of having to type that on, it's really easy to just Control D. Notice the formula here was A2 plus 1. That's not what we actually typed in. Well, we clicked on the cell and it said A2, right? Plus 1. But now look at this. A3 plus 1. So even though it says right here in the definition, undo. Even though in the, people, what have you done?
Just change it back to 2. Change it back to
Undo. Notice how this says A2, this says A3, this says A4, this says A sub 21 plus 1. This one, this cell plus 21. Okay, having said that now, let's look carefully how we're going to set up our recursive definition. Now, that was not the actual recursive formula. That was just generating the natural numbers from 0 up to infinity, where in this case 20. Now we're actually doing our recursive sequence, which was what? Start with equals. Take the population. That's the previous population. Multiplied by 1.01. Add on 20,000 immigrants. Boom. And there's our next population. Now we control D down. And there you go. That should agree, right? Okay. That's the spreadsheet approach. You don't have to do this on the test, but I encourage you to do this if you're presenting a homework problem like this. You show us the spreadsheet along with your show what you use for a formula. Okay? Yes.
How do you want us to annotate it? Like,
How could you annotate this? I'd say right here, you might want to say the formula is let's look at it. It equals B2 times 1.01.
Would you say B2 or would you have to say B minus 1?
I would just use the notation of the use the notation of the spreadsheet. And this is, when you do this, when it says B2, it's relative referencing. So even though it says B2 here, it's thinking in terms of its computer memory that you're referring to the cell just above B3. So you're always going to refer to the cell just above the current one you're looking at. Okay? All right. Great. All right, back to the notes. Picture on. Because now we have to look at a little Fibonacci. What happened to my little camera?
Yeah.
Did you say Fibonacci?
Yeah.
What's Fibonacci gonna use?
Fibonacci's number. Yeah. That 8th grade. Do you remember? You don't remember that? Let's get class together.
no, you weren't. I think we were in the other class.
I don't know why I put all those extra things in, but that's the idea, okay? There's our spreadsheet. Okay. Here we go, with the Fibonacci sequence now.
Fibonacci.
You actually define it recursively, but in terms of two initial conditions.
Oh my.
Okay? So let's see how this works. T sub 3 then is T sub 2 plus T sub 1.
Want to see how many digits?
So that's 1 and 1, which is 2. T sub 4 is T sub 3 plus T sub 2. 2 and 1 is 3. T sub 5, T sub 4 plus T sub 3. T sub 4 was 3, T sub 3 was 2, and we get 5. Let's speed this up with our wonderful calculators, right? Yeah, here's your TI-DNI approach. Let's try it. I have a spare calculator here if you're in need. Okay. Enter one answer. Now, how do you get this? Cosmos tells you just put a plus here, but how do you get the answer 2 then?
Alright, so.
If you wait, the calculator's not going to suddenly say, okay, you mean the next one? No.
Oh no, that's not what I did.
Could you just
Oh, you make
Could you
another
just
answer.
type in answer 2?
You can type it in. You can also find the answer thing at the bottom there.
Oh my god, I got it.
Where's the answer?
Switch it to 2. Yeah, you gotta make sure it says 2. And so this is stepping backwards. It's saying the answer 1 before the current one you're working on. So that's the current, that's that one. Plus the answer 2 before the one you're working on. Okay?
Keep getting 1.
Dude, you know what's cool with Fibonacci?
Keep getting
Wait.
No, you get answer 1 plus answer 1 probably. I don't
No,
know.
I'm answer 1. Oh, times.
Times, that won't do it. You need plus. Otherwise, it's going to go 1 times 1 times 1 times 1.
Is Fibonacci from Italy?
I believe so. I'm sorry, I didn't put a picture in here.
He's Spanish.
Okay.
Alright.
If we have some time, we'll look that up, Chuck.
What's the next number 2?
So let's see. What did you come up with then?
1.
1, 1.
2,
3, 5, 8, 13, 21, 34, 55, 89, 144.
Congratulations, you can read up here.
What's so special about this number?
It's
12 square and
doesn't is a growth.
Oh.
It's nice to know that's in the Fibonacci sequence. Now, the spreadsheet approach is very important because you can quickly do another little trick on this. So let's head to our spreadsheet and come up with a new one. So, here's our sequence right away. I'm just going to jump right into the sequence and not bother. Well, no, let's get the term number 2. It's called the index. Pointing to the term in the sequence here. Let's have this equal previous term plus 1.
Command D for control.
Control D. And then we're going to call this the Fibonacci sequence. Fibonacci sequence. The values of it. Goes 1, 1. So we had to initialize 2 things here now.
Do some programs just like recognize it if you type that in?
Fibonacci sequence.
Yeah, like does.
Some. So now we want to take the previous 2 terms and add them up. And control D, and that should, okay.
Oh my god, so
So, is this arithmetic?
No.
Are you sure?
Yes.
How do you tell?
0 and then 1 and then
There's not a common difference.
Well, let's just check.
it's 0.
Oh yeah.
What can you tell me about the common differences?
They add up to get the next one.
They are a Fibonacci sequence of things, right?
Fibonacci sequence.
Because that's what you do in a Fibonacci sequence. You're basically, the difference between the previous 2 terms is that, difference between these 2 terms is actually this term before it, okay? All right. Okay, so is it arithmetic? Arithmetic question mark? No. Is it geometric? Is it geometric? Let's get a question mark on there. Ratio of 2 successive terms. Class?
Hey, look, doesn't that look
Is it geometric?
No.
That's the golden ratio.
You were just talking about that.
Okay. Yeah. So even though it's not geometric, it's trying to act like a geometric sequence.
trends?
And notice you got that number down, 1.618.
Yeah.
03399.
Yeah.
How about if I change my first 2 numbers, like to my old address, 1220 West Ferry Casimir?
You're gonna go to your old house.
Still the same. Sort of.
Still approaches the same features. This is the amazing thing about the Fibonacci sequence. You don't actually have to start with 1 and 1 to get that ratio to be approaching the golden mean. I don't know. We'll look it up later. Okay. So it's not geometric, no, but the ratios approach the golden mean. Okay? All right. Back to the notes. Back to the notes, people. Let's take a picture of your beautiful sequence.
The light is still on.
Excellent. Capture. For some reason it leaves this little, I don't know why it does that. Okay. Thank you for your patience. We did a little extra with the spreadsheets today. There's our spreadsheet approach. Okay, now to the notes. There actually is an explicit formula for the Fibonacci sequence. Would you like to see it? Oh yeah, that's one thing I didn't realize. This little screened thing is nice. It only shows up here. It doesn't show up on the other thing.
Oh no.
Yeah, there it is.
Oh my goodness.
Where sure enough, this golden mean, oh I'm sorry, also known as the login amen.
That's funny, because logged in is a combination of
Golden. Mean. Okay, there you go.
Oh my god.
Let's just make sure you're not blindly copying it up.
Yeah.
Things that everyone think of it, okay? But the golden mean shows up in here, and you can try that sometimes on your calculator. Like try putting in like that 12th term or that gross term.
Yeah, that's it.
See what you come up with.
Wait, is it actually called logged in on Matter, or did you just make that up?
That was a little exercise, but you guys guessed it way back, okay? You kind of ruined the fun.
Oh, I like these.
Don't stare too long because it starts shifting.
It is.
Oh, that's so cool. That's so great.
Well, here's the extra credit. Print this up and then count the spirals in one direction. This is why I'm sure you did this with sunflower seeds when you were a kid. You know those big sunflower heads?
Yeah, I grew
And
one.
you look at the seeds, and then count the spirals going one way, and then count the spirals going the opposite direction.
Do it on pineapples too.
I think you'll find something very interesting.
Oh wait, they have the same amount of numbers.
Now-
No way.
Now,
No way.
let's hold it. I want to end here with something from, check this out now. Wikipedia is our friend. Where did it go? Oh no. The internet's down.
No, Google's down.
No, let's look up Fibonacci sequence.
I don't know. It's scary. Try to Google it.
I'll use my stuff.
Google birth control or I tried to Google Google.
Okay. I'm sorry, John, no picture of Mr. Fibonacci, but I wanted to show you this. Decomposition of powers of the golden ratio. Recognizing Fibonacci's common notorial identities. Other identities. Check these out. You know, in the Fibonacci sequence, we talked about how any one term is the sum of the previous two. But here's Catalan's identity, Cassini's identity, Cogni's identity, Lucas numbers, spelled with a C, sorry. But you can take any one of these then and investigate it with a spreadsheet to see if it's true and verify it. Like any term squared minus, look, you go back, you go forward R in the term sequence, you go backward R in the term sequence, and you get this. Now, how do you discover this?
By
Just got
being
the numbers so
geniuses.
often that you know these patterns.
You just went, oh, look at this number, look at the number just forward and the number down here, and sure enough, it's like the difference squared times -1 to the n minus 1. Okay? What are some of the other ones on here? Oh, here. The 3nth term is all that. All right? So knock yourself out of that, for some extra great tips and so forth.
Wait, what are we
Okay.
supposed to do?
Roger, identity.
Yeah.
Mr. Lane,
Thank you.
what are we
No, you know, I'm not saying prove it. I'm saying take a spreadsheet and verify these. Go down about 100 terms real quick on a spreadsheet, and then you can identify these other things, right? Now, something when they talk, these are easier on a spreadsheet. This one's going to be a little tricky when you have to talk about this extra index of R. Okay? But that's something you can work on a spreadsheet, 2x2 spreadsheet then, too. Right?
I would like to do that.
So let's investigate that. I will cut and paste the page there, so you got something to look at here. Oh, look at it. Let's get this trick up in here too. That if you take the sum of the first n terms of the Fibonacci sequence, square them all, it's the product of two successive terms. That's a nice quick one that you can check out too. Let's see if that makes sense. If we add the first n terms of the Fibonacci sequence, it should end up being the product of the current terms times the previous term. Do you buy that?
Yep.
Don't be so.
Wikipedia told me so.
Wikipedia told me so. God.
Wikipedia's always right.
Let's check that out over here.
It was a screenshot.
Here's your Fibonacci sequence, right? What do all these add up to?
The next term.
8, 10, 11, 12, right?
Yeah.
Which is the product, it was supposed to be the product of? Wasn't it equal to the product of the previous two terms?
3 and 2.
5 and 3, that doesn't work.
Oh, you gotta square them.
Yeah.
You squared them all and add up that. 1, 1, 4, 9, and 25. That adds up to 10. That adds up to 40. Right?
Yeah.
5 times 8 is 40.
Oh, are you good?
Does that work throughout the system?
Let's add another one, 64. Now you're up to 144.
104.
Yeah.
A 104.
8 times 13.
Yeah.
8 times 13 is 104.
8 times
Wow. Okay, a lot of amazing things in there. Okay. That's it. Now I'll post the sign-up sheet. You got just enough time to sign up, okay? Stop.
Well, no one else.
Stop the video. Stop.